In this lecture, we're going to explore the structure of materials at the most basic of length scales, namely the atomic scale. It's an interesting experimental fact that the vast majority of materials or solids that's currently known occur in crystalline form, meaning that the atoms that the material is composed of are arranged in a regular pattern in real space. The reality of this regular arrangement of atoms in a crystal was first convincingly demonstrated by the X-ray crystallographers. This body of work goes all the way back to 1913, due largely to von Laue and the father and son Bragg and many other workers. Let us start with the most basic of definitions that describe a crystal, which you can see at the top of this screen. Namely that a crystal can be viewed as a combination of a lattice and a basis. Let's define what these two things are. The lattice is essentially a mathematical construct, and it is a collection of regularly or periodically spaced points in space, in real space. And the basis is nothing but a collection of one or more atoms of one or many different types associated with each lattice point. Let's write these things down. Okay, so there we have it. The lattice is a mathematical construct and the basis is a collection of one or more atoms associated with each lattice point. And together, the lattice and the basis define the crystal. Let us now illustrate this using an example in 2D or two-dimensional space. And we're going to use this example to define some basic notions, basic concepts. Okay, so here is a two-dimensional lattice, essentially a collection of points in this two-dimensional space, regularly spaced points. And bear in mind that this is not a crystal yet. It's only a lattice, as we have not really associated one or more atoms with any of these lattice points. So at this point, this is just a mathematical construct, a collection of regularly spaced points in two-dimensional space. Now we are going to use this lattice to define some important concepts, as I just said. One way to define a lattice mathematically is by using these things called unit cells. I'm sure many of you have heard of unit cells, and let me give some examples of unit cells. I'm just going to draw one possible unit cell that can define this lattice. So there it is. So that's a unit cell. The interesting thing about unit cells is that when they are translated periodically, they can actually replicate the entire lattice. In other words, you can tile this two-dimensional plane with this rectangular unit cell and recreate the entire two-dimensional lattice. Let's make an important and interesting observation here. In fact, let me ask this question. How many lattice points does this unit cell contain? If you think about it a little bit, you will realize that it contains two lattice points. It is easy to figure out why there are just two lattice points per rectangular unit cell. The four lattice points at the corners of this rectangle contribute a quarter lattice point each to this unit cell, and the one at the center contributes an entire lattice point. And so that's a total of two lattice points per cell. Let me draw another example of a unit cell, and I leave it as an exercise to figure out how many lattice points this contains. Right? So this is another example. And here is another one which is very special. because it contains exactly one lattice point per cell. And for this reason, this smallest unit cell that I just drew is called a primitive cell. Let me write this down. So to reiterate, the primitive cell is a special cell which is the smallest possible unit cell you can imagine for a given lattice, containing exactly one lattice point. While we are in this topic of primitive cells, let me now introduce a new cell, namely the Wigner site cell, which turns out to be a very special type of primitive cell. It turns out that the Wigner site cell is the most spherically shaped primitive cell you can possibly imagine, and its construction can be explained in this manner. Consider any lattice point. Let us say we're considering this particular lattice point, and consider the nearest neighbors of that particular lattice point, which in this particular case happens to be these six other points. Next, let us consider the line that connects our original lattice point to the six nearest neighbors. Let's draw one of them. And let's now create a perpendicular bisector of that particular line, which I'm going to draw in red, which is like that. Likewise, we draw the perpendicular bisector for all the other lines that connect our original lattice point to the nearest neighbor lattice point. And when you do that, you get this nice looking hexagon for this particular lattice. So this hexagon is essentially the the Wigner site cell for this chosen two-dimensional lattice. So this is our Wigner site cell. So the Wigner site cell, as I mentioned earlier, is the most spherical primitive cell you can imagine for a given lattice. And interestingly, it also displays the full symmetry of the underlying lattice. In this particular case, it's a hexagonal symmetry that is actually revealed by the construction of this Wigner site cell. Using this two-dimensional lattice and the unit cells we have constructed so far, let me introduce another set of interesting and important concepts, namely the concept of unit vectors, which I am going to draw now for one of our primitive cells using blue lines. So I'm labeling these two unit vectors, A1 and A2, and because this is a two-dimensional lattice, we need two vectors, two such unit cell vectors to completely specify our unit cell, and by extension, the entire two-dimensional lattice. Let us now make two important observations. The first one is that all the lattice points are equivalent. And the second one is that given any reference point, any reference lattice point, we can reach any other lattice point through a vector which is a linear combination of these two unit vectors A1 and A2. So R is a new vector which can connect any lattice point to any other lattice point. And of course L and M are integers and A1 and A2 are original unit cell vectors. We are going to use the notions we have learned so far and move on to three-dimensional systems, and throughout the process we are going to keep introducing newer concepts. The first one is this thing called the Bravais lattice. So Bravais lattices are essentially a collection of lattice points periodically arranged in space, in this particular case three-dimensional space, where all lattice points are equivalent and any lattice point is reachable from any other lattice point in a manner that we have just discussed with the example of the two-dimensional lattice. So R is what is called as a translation vector, which connects any lattice point to any other lattice point via the three-dimensional unit vectors A1, A2 and A3, and of course N1, N2, N3 are integers. It turns out that there are 14 distinct Bravais lattices one can imagine in three-dimensional space. 14 different and distinct Bravais lattices in three-dimensional space, which can all be organized into 7 crystal systems. We are now systematically going to look into the 14 Bravais lattices and the 7 crystal systems, and we'll try to understand what is different about these different cases. So before we dive into the 14 Bravais lattices and 7 crystal systems, let us make an important observation. In three-dimensional space, a unit cell may be defined in terms of the three unit cell vectors, A1, A2, and A3, and we have indicated that those are vectors by putting arrows at the top, right? So A1 vector, A2 vector, A3 vector, they have those arrows in the top. Now those three quantities can actually be traded off for 6 other quantities, 6 other scalars. The first 3 are the magnitudes of the 3 vectors A1, A2, A3, which we just represent as A1, A2, A3 without the vectors on top. And the 3 angles, alpha 1, 2, alpha 2, 3, and alpha 1, 3, which are essentially the angles between any 2 unit vectors. So the bottom line is that the 3 vectors A1, A2, A3 can be traded for 6 numbers. A1, A2, A3, the 3 magnitudes, and alpha 1, 2, alpha 2, 3, alpha 1, 3, the 3 angles. With these definitions in place, we are now going to go and take a look at the 14 Bravais lattices and 7 crystal systems and see how these 6 numbers, alpha, the 3 alphas and the 3 A's, vary with respect to the choice of the crystal system or the Bravais lattice. So that's the next step. So here they are, the Bravais lattices and the crystal systems. So as we just mentioned, there are 7 crystal systems, which are also called as crystal classes. The most general and the least symmetric of those 7 is the one that's called the triclinic, which is what is listed at the very top. And the triclinic system is defined as the crystal system where the magnitudes of the 3 unit vectors A1, A2, and A3 are not equal to each other, and the 3 angles that we just defined earlier are also not equal to each other. So that's what is stated over there. The other crystal systems are systematically more symmetric than the triclinic. For example, the monoclinic system, which is the second one in this list over here, is again composed of unit cells that the magnitudes of whose unit vectors are not the same. A1 is not equal to A2, not equal to A3. But 2 of the angles are equal to 90 degrees, and the third one is not 90 degrees, something that's other than 90 degrees. That's the monoclinic system. So that's, in some sense, a special case of the general triclinic system. And the next in line is the orthorhombic, where the magnitudes of the unit cell vectors are all different from each other, but all the angles are 90 degrees. Tetragonal is more symmetric. All the angles are 90 degrees. 2 of the unit cell vectors have the same magnitude. A1 is equal to A2, but A3 is different from A1 and A2. Going further down the list, we got the trigonal system, where A1 is equal to A2 equals A3. And all the angles are also equal, but they are all less than 120 degrees. So that's the trigonal system. Moving next to the list, we come to the cubic system, which happens to be the most symmetric of them all. A1 equals A2 equals A3, and all the angles are equal to 90 degrees, creating a cubic unit cell. And then last in the list is this hexagonal system, which actually should probably be placed a little bit ahead in this list, because it is not really necessarily more symmetric than the cubic system, but in this list it's listed as the last, but no matter. So in the hexagonal system, A1 equals A2 and A3 is something different. Two of the angles are 90 degrees and one of them is 120 degrees. And this basically leads to hexagonal lattice. So those are the 7 crystal systems or crystal classes. Note that some of these crystal systems have multiple unit cells depicted. For example, if you look at the monoclinic system, you got 2 choices for the unit cells, right? One that is called simple or primitive. The P up here represents primitive. That's a primitive unit cell. And then you got another one over here, which is volume centered. So you have lattice points at the corners of the unit cell, at the vertices of the polyhedron that forms the unit cell. But there is also a lattice point at the body center or the volume center, which is why it's called the volume center. Likewise, the orthorhombic system has 4, right? So there is a simple or the primitive, there is a volume center or body center, there is a base center, right? There is a base center, and then there is of course the face center. And likewise, if you jump ahead to the cubic system, you got 3. There is the simple cubic, which is primitive, and then there is a volume centered or body centered, and then there is a face centered. Now, if you count up all of these unit cells that are shown over here, you will find that there are 14 of them, right? So there are 14 pictures up here. Those are the 14 Bravais lattices. It should be borne in mind that not all 14 pictures that you see here represent primitive cells. Only 7 of them are primitive cells and the other 7 are not. However, it should be noted that even those other 7 which are not primitive cells, the way it is pictured here, they can be represented in terms of primitive cells and unit vectors corresponding to those primitive cells, which is what really makes them Bravais lattices. So we're going to finish up this lecture with a brief discussion of space groups, which I'm sure many of you have heard of. So far in this discussion, we've been mainly concerned with translational symmetry. We mentioned that a unit cell can be defined, and if the unit cell is translated along the unit vectors, you can essentially recreate the entire lattice. You can tile space, 2-dimensional or 3-dimensional. And we also mentioned that you can go from any one lattice point to any other lattice point through a translation, which we had defined earlier in terms of the unit vectors. So all that deals with translation. But crystals also can have other types of symmetry, such as rotational, inversion, and reflection. So the rotation, inversion, and reflection symmetries are captured by what are called point groups. So the translational symmetry combined with the point group symmetry gives you what are called space groups. So the point group symmetry is also referred to as point symmetry by some people. And for an isolated system or a molecular system where translational symmetry is irrelevant, the number of point group symmetries possible is really infinite. So let me at this point mention what we really mean by group or point group. A group is really a collection of operations that leave a system invariant or unchanged. So if you have a particular molecule, let's say H2O, it has a certain set of symmetry operations that will leave that particular molecule invariant. For example, if you take the plane that contains the H2O molecule, reflection of the system of the molecule with respect to that plane will leave the molecule invariant. So that's one symmetry operation that leaves the system invariant, and it's an operation that's part of the group, symmetry group that represents that particular molecule. Another one could be a plane that actually bisects the molecule, and again reflection with respect to that plane would leave the molecule invariant. So an in-depth discussion of groups or point groups is really beyond the scope of what we are discussing here. And so I just want to mention that a group is really a collection of symmetry operations that leave the system unchanged. Now, for an isolated molecular system, as I mentioned earlier, there are, infinite number of possibilities that could leave a particular system invariant, and so there are, in principle, infinite number of point groups. However, when you combine that with translational symmetry, there are only 32 point groups that are compatible with translational symmetry. So each of the 32 point groups is associated with a crystal system or crystal class, and the combination of point groups and translational symmetry leads to a total of 230 space groups. And each of the space groups is essentially a collection of symmetry operations, translational as well as rotational, inversion, reflection symmetry operations that will leave that crystal unchanged. In fact, any crystal, now we're really talking about crystal, which is a lattice plus basis. So any crystal can be placed in one of these 230 space groups. So it's really quite incredible that all the infinite possible crystals can actually be put in one of these 230 classes. That concludes our lecture for today. Thank you.